Hello, my name is Dr. Ibrahimian and this is the first video on my single variable calculus 2. In this video, we're going to talk about the first application of the integral. So let's first remember how we evaluated an integral and what it meant to evaluate an integral. So the integral from a to b gives us the area underneath the graph of a curve y equals f of x from a to b. So what do we do to approximate the area underneath the graph of this function? What we do is we take the interval from a to b and we divide that interval into small pieces. In each of these intervals, we pick one sample point. So we start with x0 and we end at xn. In each of these, we pick one sample point. So let's say this is xi minus 1 and xi. We take one sample point, and based on that, we create a rectangle. So we create this rectangle. So as you have seen in single variable calculus 1, you could take the left endpoint, midpoint, or the right endpoint. Those are the typical examples of approximations of integrals. And then we take the area underneath the graph of the function and approximate that by the sum of the areas of these rectangles. So the base of this rectangle is xi minus 1, which I denote that by delta xi, and the height is f of zi. So I take the base and times height, so we get f of zi, which is the height, times the base, which is delta xi, and we take the sum. That would be an approximation for the area underneath the graph. Then we allow delta xi to approach 0, and that would give us the value of the area underneath the graph of the function y equals f of x from x equals a to x equals b. Now, if we are doing the same thing in three-dimensional space, that means we have some object in three-dimensional space. Let me draw that down here. And this would be our formula, which I will talk about in a minute. So we have some object in three-dimensional space. This is the x-axis, this is the y-axis. Our object is between x equals a and x equals b, but it's something in three-dimensional space. It could be something obtained by a rotation, or it could be basically any object in three-dimensional space as long as it is bounded by these two values, x equals a and x equals b. So how do we evaluate the volume of this? We can do something very similar. So we can take the interval from a to b, divide it into small pieces, and for each of these, we can approximate this by a cylinder. So we can take some cylinder here, and we can add up the volumes of this cylinder. So the volume of a cylinder is base area times height. So what is the base area? And by the way, the graph that I have is not quite accurate. The base is on the other side. So the base is right here. This is our base of these cylinders. And the height is here. So let me draw that again. So we have a base here and a base here, and this would be our height. So this would be our height. So our height would be delta xi. If I call this one xi minus 1 and this one xi, that would be delta xi. And the area of the base would be just whatever the formula is for the area of the base here. This looks like a circle, so it would be pi r squared, but it depends on where we are. And it depends on what the cross sections are. So let's assume that a of x is the area of each cross section. Then we can take a of x multiplied by height, which is delta x, take the sum and allow delta xi to go to 0. So that eventually gives us that the volume is the integral from a to b of the cross-sectional area dx. So based on that, we're going to talk about a couple of examples. We will do 3 examples on that. The above formula is called the cross-section formula for the volume. So let's start looking at example 1.1. Find the volume of the solid obtained by rotating the region between the curve y equals x squared and the x-axis with x between 1 and 2 about the x-axis. So we have x equals 1, x equals 2, and then we have the graph of y equals x squared, which would look like this. So this is our region, and we rotate this about the x-axis. So when we rotate this about the x-axis, we're going to get something like this here, and a disk on this side as well. So we get a shape like this. Now we want to find the volume of this shape. So we have to find the cross-sectional areas, and then we have to integrate that dx. So if I call this point x, what is the cross section? So each cross section is a disk. And what is the area of a disk? It is pi r squared. So we have to find out what is the radius of these disks. So the radius is this height right here. Now note that the graph was y equals x squared. So it's the y coordinate of that point, this point right here, which is x comma x squared. So that means the radius is in fact x squared. So that tells us that the area of the cross section is pi r squared, which is pi x to the power of fourth, which means the volume is the integral of pi x to the power of fourth dx. And this is dx because we are looking at these cross sections that are perpendicular to the x-axis. The limits of x are 1 to 2 because that's what they gave us. And then we can go ahead and evaluate this integral. X to the power of fifth over 5 from 1 to 2. This is pi 32 over 5 minus pi 1 over 5. So 31 over 5 pi is our final answer. Let's look at two more examples. So the next example is a little bit different. Let R be the region that lies between y equals x squared and y equals 2 minus x squared. So let's draw the diagram for this. So y equals x squared looks like this. Y equals 2 minus x squared is an upside down parabola, and the vertex is at 0, 2. So it looks like this. So this is our region R. So now we rotate this about the x-axis. This is again, rotation is about the x-axis. And we want to see what shape we're going to get. Well, the shape that we're going to get is we rotate this one and we rotate this one. So as you see, there is a hole here in the solid. So any cross section that we get, if you take this point X, you're going to have like a hole right here and then a larger circle here. So what's the cross section? The cross sections are these washers. So each cross section is a washer. Now, in order to figure out the area of each washer, we need to find the inner radius and the outer radius. So what is the inner radius? The inner radius is y equals 2 minus x squared, or rather y equals x squared. It comes from that function. And the outer radius is y equals 2 minus x squared. Let me use a different color. So this is our inner radius, and this would be our outer radius, which is why the inner radius is y equals x squared, and the outer radius is obtained from y equals 2 minus x squared. So this would be x squared, and the outer radius is 2 minus x squared. Now, and this is the cross sections that are perpendicular to the x-axis, so we need to find the limits of x. So the limits of x are the intersection of the two curves. So the intersection is y equals x squared and y equals 2 minus x squared. From here we get x squared equals 2 minus x squared, which gives us 2x squared equals 2. So we get x equals plus or minus 1. Now that we have the intersection, we can set up the volume. So the volume becomes the integral from -1 to 1 pi outer radius squared 2 minus x squared. That's the area of the larger disk minus pi x to the power of 4 x squared dx. And then we're going to go ahead and evaluate the integral. Let's first, for simplicity, factor pi. We get integral from -1 to 1, and then square that. We get 4 minus 4x squared plus x to the fourth minus x to the fourth, all of that dx. So x to the fourth cancels, and we can integrate this pi times 4x minus 4x cubed over 3 from -1 to 1. Pi times plug in 1, we get 4 minus 4 thirds minus plug in -1, we get minus 4, and then plus minus 4 thirds. And you can simplify this or not. So typically I don't really expect the students to simplify things in this class unless it is specifically specified. Now, what is the general idea here? The general idea is that if you have a curve, a region between two curves, so we have two curves, y equals f of x and y equals g of x. So we have these two curves. The top one is y equals f of x, and the bottom one is y equals g of x. And we take this one and we rotate it about the x-axis. So we rotate this region about the x-axis. So we're going to get washers. The inner radius would be g of x. So this would be g of x is the inner radius, and the outer radius would be f of x. So this would be our outer radius. And we can find the area of each cross section by taking pi inner radius outer radius squared minus pi inner radius squared, and then integrate. So this would give us the formula, and the limits are assumed to be a and b. This is the formula for the volume, and this is called the washer method because those cross sections are washers. One last example, and then I'm going to summarize what we did. Let R be the right triangle with vertices. So again, let's draw the diagram. So we have a right triangle with vertices 1, 0, 0, 2. So this is the right triangle. The base of a solid E is R. So we have a solid whose base is R. Each cross section of E perpendicular to the y-axis. So cross sections perpendicular to the y-axis are semicircles. So they look like this. These are cross sections. So it's in three-dimensional space. It comes out of the screen, and it is perpendicular to the y-axis. And each of them are semicircles whose diameters lie on R. Find the volume of E. So again, we'll have to find the cross-section area. But because we are looking at cross sections perpendicular to the y-axis, we'll have to integrate with respect to y. So let's just start with some y, and let's figure out the area of this cross section. So what is the radius? The radius of the semicircle is half of this length, which is x. So this is x, so it's x over 2. So the first thing I need to do, I need to write down the equation of this line. So the line is, okay, y equals, what is the slope? The slope is rise over run. So rise is 2 and run is -1. So it is -2. And then what is the slope? What is the intercept? This intercept is just 2. And you can easily see that if you plug in 1, you get 0. And if you plug in 0 for x, you get 2 for y. So this is in fact the line going through that. So I have to figure out what x over 2 is. So I'll solve this for x. I would get x equals 2 minus y over 2. I added 2x to both sides and subtracted y from both sides, and then I divided by 2. So this is our x, which means the radius is 2 minus y over 4. So this is our radius. So that tells us that cross-sectional areas are 1/2 of pi r squared. So that's the cross-section. Now we'll have to integrate this. So the volume would be the integral from 0 to 2, because we are doing cross-sections perpendicular to the y-axis. They are going to be from 0, which is the bottom of the region, to 2, which is the top of the region, times the cross-section area, 1/2 pi 2 minus y squared over 16 dy. And finally, we'll have to integrate this, which we have all these constants, we can take them out. So pi over 32, integral from 0 to 2. We can expand this. We get 4 minus 4y plus y squared dy. Although there's a trickier way of doing this problem without expanding. I'll explain that after I'm done with the solution. And then we integrate this. We get 4y minus 2y squared plus y cubed over 3. And this would be from 0 to 2. And I'll let you substitute these. This is pretty straightforward. Now, an alternate way of evaluating this integral, which would have made things easier, would be this. Or you could do the integral. So it's pi over 32, integral from 0 to 2 of 2 minus y squared dy. Is an alternate way of doing this. Do a u substitution. U equals 2 minus y. That gives us du equals minus dy. So this becomes pi over 32 integral. This is u squared. Dy is negative du. And the limits of integration are going to change. When y is 0, u is 2. When y is 0, u is 2. When y is 2, u is 0. And this is easier to integrate. This is minus pi over 32, and then u cubed over 3 from 2 to 0. Now, if you plug in 0, you get 0. If you plug in 2, you get pi over 32 times 8 over 3. And that is very easy to evaluate. So after simplifying, we get pi over 12 as the answer. And it should be the same thing here. So let's actually do the computation here, see if it matches. We get pi over 32. Plug in 2, we get 8 minus 8 plus 8 thirds. And then when you plug in 0, you get all 0. 8's cancel. You get pi over 12, in fact. So yes, it does match. To summarize, when you are solving a problem on volumes, always draw a diagram before solving the problem. And volume is the integral of the cross sections. And the washer method allows us to compute the volume using this formula. So this brings you to the end of this video. I will see you in the next video.